Hello everyone. This is part 3 of carbocation chemistry, which is stability of carbocation. But it is suggested to watch the previous two videos, part 1 and part 2, because the sequence of parts are maintained in such a way so that you can comprehend it easily. You can find that in the description box, that is a playlist link of carbocation chemistry, or you can click on the link appearing on the screen. Why we should discuss the stability of carbocation? Because as a reactive intermediate, it has direct effect on the reaction. Now what are the factors which are important to know if we want to check its stability? So here the 4 points are mentioned. But I am not saying that only these 4 points, that is stability of carbocation, is restricted to these 4 points. That is not always correct. There may be some other factors depending on the structure of the compound, that is the structure of the carbocation. But these 4 points are the most important points that we should consider. Now here the first 3 points, that is neighboring carbon atom, then neighboring CC multiple bond, it may be CC double bond or triple bond, then neighboring atoms with lone pairs. The first 3 points are basically related to some donation effect. So that is why here it is mentioned neighboring for all these 3 points. Neighboring carbon atom, neighboring CC double bond or triple bond, and neighboring atoms with lone pairs. Now as carbocation is electron deficient species, so obviously it is common sense that if there is some group just beside it which can donate electron density. Now this type of donation, it may be in different forms. It may be through inductive effect, hyperconjugation effect, it may be through resonance, or it may be that if there is some if there is some lone pair present. So any electron donating effect, obviously it will stabilize the carbocation. And on the contrary, if there is any electron withdrawing group present, for example cyano, NO2, C double bond O, it will destabilize it. But what are the factors that will destabilize? I am not going to focus on that part. Focus will be only on some electron donating effect. And the last point, which is aromaticity, it is completely different from these three. So all this will be discussed in detail. The first one, neighboring carbon atoms. So neighboring carbon atoms, here you can see 3 degree, 2 degree, 1 degree methyl. All the 4 types are given. Now this is based on classification of carbocation. If you have any doubt on that, so you can watch the previous video, that is the classification of carbocation. And for that you can click on the link appearing on the screen. So for 3 degree there are total 3 methyl group, the example that we have taken. Then as we are moving from 3 to 2, there are 2 methyl group, then only 1 methyl group. So here what is happening? You have to consider plus I effect. So we know when we consider any alkyl group, there is plus I effect. So here is the number of alkyl group attached to C plus, more will be the stability. So that is why as we are moving from 3 degree to 2 degree to 1 degree, gradually the number of alkyl groups are decreasing and also stability is decreasing. So plus I effect, which is a kind of donating effect, that is increasing as we are moving from right to left. And the last one, there is no alkyl group, it is simply methyl, so it is very unstable. So the first reason is basically inductive effect, that I have already said. And there is another reason, which is hyperconjugation. So hyperconjugation is donation of electron density from carbon hydrogen sigma bond that is present at the alpha position of the carbocation. So here this electron density from sigma bond, that will be donated to the vacant orbital of the carbocation. So from this picture you can understand, this picture is basically ethyl cation. Suppose I am writing it here, total 3 CH bond, and then there is CH2. So you can consider any of this sigma bond. So the electron density that is present here, that is donated to the empty p orbital of the carbocation. So obviously higher will be this type of number of alpha hydrogen. Why I am calling it alpha hydrogen? Because this is alpha carbon with respect to C plus, and all these hydrogens are alpha hydrogen. Higher is the number of alpha hydrogen, more will be this type of effect. That is the reason, if you look at these two examples, the first one is basically Me3, the first one is basically Me3C plus. Where 9 alpha hydrogens are present, all the alpha hydrogens are here shown with bold bond. You can see these are the alpha hydrogens. But if you consider the second example, which is basically Me2CH CH2. So here number of alpha hydrogen, it is only 1. So that is why this will be more stable compared to the second one. Come to the second point, which is neighboring CC multiple bond. Carbocations adjacent to any CC double bond or triple bond, there will be some special type of stability, and it is because of the overlap between the empty p orbital of the carbocation, because we know there is empty p orbital. Remember the structure of carbocation. So this empty p orbital and the p orbital of these multiple bonds, that is pi bond. In these two there is pi bond present. So these two p orbital, there will be interaction, and this pi electron density that will be donated to the empty p orbital. Okay. So here we have taken this example, which is allyl carbocation. Now this carbocation, here conjugation is possible. So this pi bond, now it will be donated to this newly generated carbocation, will be now this carbon. See, first the charge is here, after shifting of this pi bond, now the positive charge is here. So if it is structure number 1, this is structure number 2, this will be the average structure of these two, where the electron that is the bonds are shown in dotted line. Another very common example is benzyl cation. So benzyl cation also, here these double bonds present in benzene ring that can take part in resonance. In this way you can have all these different resonance structures, and the last structure, that is the average structure. That is why dotted lines are shown. Now you can see both these examples, positive charge is present, it is actually 1 degree, isn't it? And from the previous point, we have seen 3 degree more stable, then 2 degree, then 1 degree. Here it is 1 degree, but still they can be stable. Now this is because of this adjacent double bond. So this is such a stabilizing influence that even 1 degree carbocation, usually very unstable under normal condition, that can also be stable if this type of effect is present. So that is the reason, here look at these two examples. Here double bond is present at adjacent position, not just any position, it has to be present at proper position. Now these two structure actually same, only difference here you have this bond. So that is why it is more stable. Similarly the second one, this is benzyl carbocation. Here we do not have any double bonds, it is not benzene ring. So that is why the first one is more stable. So that is all about this point. Come to the third point, another kind of donating effect, but now lone pairs will be involved. So a neighboring atom with a pair of electrons, for example it may be oxygen, nitrogen, sulfur, halogen, at correct position. So it is not important that mere presence of ONS halogen, it will stabilize it. No, it can donate lone pair only it is present at the correct position. This point is very important. Now at a first glance it seems they are electronegative atoms. Then why they will not show electron withdrawing effect? Obviously they will show electron withdrawing effect because they are the electron withdrawing group, and they will show minus I effect. As you have seen in case of alkyl group, there is plus I effect. So they will also show minus I effect. But remember, they are electron donating group because of their lone pairs, and that they can do by resonance. So this factor, suppose this is factor 1, this is 2, it will overcome over the first factor, that is induction factor. So that is the reason ultimately this effect will be more important. You can see from this example, here carbocation is here, this is alpha position, this is beta position. Where is oxygen present? It is not present at adjacent position, it is far from that. Or you can also have oxygen somewhere here or here. So in all these positions, it cannot show resonance delocalization. It is possible only when it is present at alpha position. Now you can see after donation there is a new pi bond present, and oxygen as it has donated, it is now positively charged. Similar structure is also possible if there is nitrogen atom present. So here it is far from it, no resonance stabilization possible, but here it is possible. If you compare these two structure, it is actually same, only difference in the first case we have chlorine. So the first one, that will be more stable, because of this type of donation effect. So here it can donate electron. So after donation there will be some double bond. Chlorine is positively charged. Okay, so that is the reason it is more stable than the second one. And the last point, which is completely different from these three, it is related to aromaticity. Any positive charge, that is a carbocation, if it is part of aromaticity, then it is more stable. Now we know that for being aromatic, these conditions must be fulfilled. That is the rules for aromaticity. It must be cyclic, conjugated, 4n plus 2 number of pi electrons, and it must be planar or flat. Now if these 4n plus 2 pi electrons are not maintained, suppose if it is only 4n pi electrons, then it will be anti-aromatic. Okay, so suppose all these three conditions are fulfilled, 1, 2, 4, but the third one is not 4n plus 2, it is 4n, then it is not aromatic. So no question of stability of carbocation, that is whether it is part of aromaticity or not, because it is not at all aromatic. So whether it is part of it, that question doesn't arise. Look at these three. In the first, all are basically fulfilling the three criteria, that is 1, 2 and 4. They are cyclic, conjugated, planar. But what about this third point? The third point is fulfilled only in these two cases, because their total number of pi electrons 2. So 4n plus 2, this format is matching where n value is 0. In the second case, it is basically matching with 4n. So it is not aromatic. Here n value is 1. And the third one is again matching with 4n plus 2, where n value is 1, because total 6 pi electrons are present. So that is the reason number 1 and number 3 aromatic, not the second one. It is also true in the second one that the positive charge, it can be stabilized by resonance. But see, it is not aromatic. So we will not consider it, whether conjugation present or not. Because when it is anti-aromatic, it is highly unstable. So just focus on the first and third. Here positive charge is part of aromaticity. So that is why it is very stable. So that is all these four different factors we have discussed. Now the important question. How do you know which factor is important when you will actually decide stability of carbocation? Suppose you have 3 to 4 examples, you are solving some problem, you have to decide the order of stability. Then which factor you will give more priority? Suppose in one example there is factor number 1 present, another example aromaticity present, then how to decide that? Now to remove that confusion, here I have a list of stability order of some different types of carbocations. I think it will help you to decide which factor to give priority. For example, you can see here this carbocation, which is basically aromatic. This example you have just seen in the last slide. This factor is overcoming, just compare with the second one. 3 benzene ring present, resonance is present. Different resonance structures are possible, but still the aromaticity factor is overcoming. Okay, now why the second one is more stable than the third one, that you can easily understand, because here we have 3 phenyl, we have 2. So in this way you can move like this. Here we have 3 methyl groups, here we have only 2. So this is 2 degree, this is 3 degree, but still because of this CC multiple bond, there is some resonance effect. So in this way we have to give priority to some factors or not, and this is a special kind of effect present. Now I have not discussed it in detail. When I will actually probably in some upcoming video I will discuss some problems, and then I will discuss why this type of structure, that is this type of carbocation where some 3-membered ring like this is present, why it is stable. Okay, so that will I will discuss in other video. So that is all about the stability of carbocation. That is the topic of this video. Okay, so we are at the end of the session. Thank you for listening.